Good morning, everyone. I'm Valérie Pittet from the DESS Unisanté, and I welcome you to the third presentation of the series Data Science for Dummies. So it will be given by Dan Assouline. And for those who do not know Dan, briefly, Dan is data scientist trained in Paris, Berkeley, and Lausanne EPFL, where he did his PhD thesis. Dan is working since June 2020 in the group we co-chair Marianne Lepogam and myself, called Health Systems Data Science in the DESS Unisanté. So Dan presented the previous session 2 days ago by introducing some machine learning concepts and frameworks and discussing differences between machine learning and traditional statistical methods. And today he will present a set of popular machine learning algorithms with practical applications in public health. And finally, he will talk a little bit about Python, perhaps Anaconda, etc., and give you some tips on libraries you can use to jump to machine learning world. So Dan, please, the floor.
Yes. Thank you, Valérie. So thank you all for being here to the third installment of our Data Science for Dummies colloque. Well, this time I'll be talking about some algorithms with some illustrations. So what is the goal of the session for you? I kind of kept the same structure as last time. The idea first is to have a broad view of some popular ML algorithms nowadays and get to know the basic ideas behind these algorithms. I won't go in very deep details because it can get complicated and it's not the idea, just broadly. And the idea is for you to get motivated to know more about them. I mean, you don't have to, but that's kind of the idea, and learn where to look to try them. So I will show you some example in Python and with some libraries for machine learning. A quick note for each algorithm. So I'll present the main idea, the general idea, good and bad points, and I'll show some comparisons of different algorithms on toy data sets so that you can see what they're good for and what they're a bit worse. For algorithms that can do classification and regression, which is the case for a lot of them, I'll present only the classification because usually it's just simpler to grasp and the idea is the same for regression, except linear regression, which I have to present because it's the ultimate benchmark, and in this case, it's regression. And for classification, I would treat only the binary case, so meaning there are two classes. If there are more classes, the idea is pretty similar, but there's some trick to go from the two classes to multi-classes problem. So this is the outline. So basically, I will go through some families of machine learning methods in a broad view. Then I'll go through different methods within the different frameworks I presented last time. So first, supervised learning methods, classification and regression. Then unsupervised learning methods, dimensionality reduction and clustering. And then I'll go through neural networks and deep learning, which can do both and are a bit separated. So I kept it as a separate issue. I won't talk about reinforcement learning because it's a bit more advanced and there's no time for that now. And then I have a short section on how do you choose the method for a problem, because there's so many algorithms, just to give you a small guide. And finally, I will show you a little bit of code. It's very, very small, and where to find some good libraries, especially in Python and in R. And then I'll summarize. So first, a broad view of the method. So for each task, I will show you a list of classical methods that I won't present now. I would present at the beginning of each section later. And then the ones that are highlighted in orange are the ones that I will present in a bit more detail. So for classification, you have, of course, some linear models, k-nearest neighbors, which is a very good benchmark in machine learning, kernel methods, and tree-based models. I will explain them again later, so don't worry. It's just for you to have a broad view. For regression, basically the same methods are adapted to regression. In this case, I will present the linear regression and its cousins, which are a bit more advanced models, ridge regression and lasso regression. And for clustering also, there's like a lot of methods. These are some methods that are common. K-means is again, it's like the one of the most basic but quite efficient. I will present it. And I will also show you one of the density-based models. Then there are, of course, probability models, which are called mixture models, and other kind of models. And for dimensionality reduction, there are basically two main families, the linear models and the nonlinear models. And I will present some of the linear models just so that you have an idea of what it does. And finally, deep learning. I will show you the basic structure of a neural network. And I will discuss kind of the few types of neural networks in general, but mostly I'll focus on the main structure and why is it powerful and very, very famous these days. So first, supervised learning. So remember, there are two types of tasks. Regression, where you try to fit a function to your data, basically, and classification, where you basically try to make groups. You want to separate between the two. This was the example I showed last time about a population of patients without Parkinson's syndrome or with Parkinson's syndrome. It could be anything. It's just the colors signify the classes. So these are the two tests. So what are the types, the families that exist for the algorithms? I will say basically in one sentence what each family does, and then I will show you in more detail some of the algorithms. So the first family is linear regression models. So you probably heard about it. Basically, the idea is to fit a line for regression. So it's a linear combination of your features. And for classification, basically find a line that separates the classes. So that's very easy. The idea of k-nearest neighbors is basically you have all your points. The value you predict for a new point, you just take the average of the close by neighbors. So it's extremely easy, but it can be quite powerful in some ways, and it can be non-linear. Actually, it's not a linear thing. So it's quite useful. Kernel methods are another type of methods, a bit more advanced, where basically when things are not linear, you try to project the data in a higher dimensional space. So let's say you go from 2D to 3D to get back to linear problem, and we very rarely have no linear problem. So in this case, it can make things much simpler, and then you go back to the 2D or to your original dimension, and things magically work out. But I will show you how. Tree-based methods are very famous as well. Basically, the idea is to successively separate your points into two parts based on a threshold. X is lower than a value or higher than a value, and you separate until you make subspaces with groups of points, basically. And the last family is like is a family of methods called ensemble methods. It's actually a global idea that just says, okay, if you have multiple models, even if they're weak, they're not very good in prediction, you can combine them and average the prediction, and it's going to be better because usually it's going to reduce the variance. And in this case, you can do it with trees because typical decision trees are quite weak models, but when you combine them together and add some randomness, it gives you random forest, which is a very efficient algorithm. So let's go through some of the models in a bit more detail. The first one is, of course, linear regression, which is originally a statistical method, and it will still be a statistical method. It's just that if a machine learning person does it now, it will maybe validate a bit differently, but the idea is still the same, of course. The idea is to fit a linear combination to the data. So let's say you have Y, your output. You want to model it as a linear combination of the features. So your features are x1, x2. You just do beta 0 plus beta 1, x1, etc., etc. This is just a way of writing it in a matrix way, but it's exactly the same. And the way to train this is to find the weights that fit the data the best. And for a linear combination, it's tradition to use one type of loss function. If you remember last time I talked about loss function, which is the squared loss. So you just say, okay, this is my reality. I just want to see what's the discrepancy between my linear combination and my linearity. So I do one minus the other. I take the square and I sum the errors. And you want to minimize that. So you want to find the betas, the weights that minimizes that. And then, so it does something like this. You feed a line. And then, of course, to predict, you just apply the linear combination to the new point, to your new point. Very easy. The weights for simple linear combination, it's actually given by a formula. So you have an analytical formula, so this is good to know, even in higher dimension. It has a classification cousin, which is called logistic regression, which is very famous. Note that even though it's called logistic regression, it's a classification case. And one of the problems with linear combination, with the linear regression, I'm sorry, is that you can overfit very easily. Remember, what happens when you overfit is you get close to the points a bit too much. In this case, for example, in this example, you might want to move, it doesn't seem like it follows a lot of the points, but actually it's the best way, otherwise you would overfit. So if it overfits, what you can do is a method called regularization, which is very, very famous. You add a penalty on the weight to reduce the variance. So you get a bit further away from the point of your training to be able to generalize it better. There are multiple versions. So the ridge regression, you basically make the weight smaller. You add a penalty to just reduce the weight. And the lasso regression, it's part of the family of shrinkage methods, very famous in statistics. You basically put some weights to zero. You just discard them, and it's a way to find values, to find features that are important in your data. So good points, of course, is very simple. It's easy to interpret, and it's a great starting point. It's usually what people start with when they do a prediction. The problem is of course, it's sometimes too simple. I mean, sometimes you just cannot fit a linear line if you don't have a linear pattern. So, but it's it's a basic algorithm, and you need to try it at some point. Okay, the next one is k-nearest neighbors. So the idea is very simple. To train, you just store your data. You just have your features and your classes. Okay, and then when you how do you predict a class for the new point? It's just the most frequent class among the training points that are the closest to the new point. And so you basically you average the values of the nearby neighbors. The question is, how many neighbors do you take? It's this k. So you need to, it's a parameter. I mean, it's a hyperparameter of the algorithm. So you need to define it. So you can use k-fold cross-validation, for example, like I talked about last time. And the distance needs to be considered. It can be a Euclidean distance, but it can be anything else. There are many different types of distances. So to give you a very quick example, let's say you have these points, you have the blue squares and you have the triangles. You want to find the class of this circle, of the disk in the middle. Well, the nearest neighbor will tell you, depending on how many neighbors you take. You see, if it's only 2 neighbors that you take, if you take k equals to 2, it's going to be a triangle. But if it's 3, it's going to be a square, right? Because then you have to go further away. So it's very sensitive to the k. The good thing is it's extremely simple, again, easy to interpret, and it can be surprisingly accurate. Powerful. I will show you at the end in a comparison. It does fairly well, even in nonlinear conditions. The problem is it's sensitive to k, to outliers, to noise, and so you need to process the data so that it works. It's quite slow because you need to store everything. And in higher dimension, it works a bit less. So yeah, but it's a good tool to have. Okay, supervector machines, which is part of the kernel family. So what is it? Basically, the basic idea of a supervector machine is very easy. You want to find a plane that separates the 2 classes so that you maximize the margin between them. What is a hyperplane? It's just a space that has a dimension -1 with respect to your current dimension. So if you're in 2D, it's a line. If you're in 3D, it's a plane, etc., etc. So once you find this plane, this is basically the first example I showed you. Remember, with the line separating the Parkinson and non-Parkinson patients. Once you have the classifier, which is a plane, one side is 0 and the other side is 1. So let's say we go back to our classical example. People without and with Parkinson's syndrome. What you do is you're gonna select the points that are further away from the group of points, and these are called actually the supervectors. And what you will do is you will find a line. So this is the margin between the 2. You want to maximize. So it's just intuitive. You want to separate them the best way possible. So you want to maximize the area without points that separates the 2 points. So you find a line that is basically equidistant from the 2 groups. Okay, and it works very well in this case because it's linearly separable. The problem is, the first case can be that, okay, you might have points, you might have blue points that are here. I mean, in the no man's land or even on the other side. There is a version of supervector machines that allow for a bit more flexibility with this, that uses another variables. I won't go into details. That's okay. The problem is if it's really not linearly separable. In this case, you know, you have something like this. So you would need to do a line like this, and this is not linear, so it won't work. Well, that's where the kernel methods, you know, take their power. How to make it non-linear? You use a function called the kernel. That's why it's called kernel methods. To describe distances. So instead of using, for example, inner products, or just to describe the distances between 2 points, you use this function. And what it will allow to do, in a vaguely said, but that's really what it does, it projects the data in a high dimensional space. So let's say you're in 2D, it's projected in 3D, where it's linearly separable. So let's say, for example, you have points like this, you have these 2 points, you want to separate them. Well, you can project them in 3D so that actually this plane separates it, and then you go back to your 2D and you have this line. So I will do a small, if you can see this, a small demonstration. So these are, you can see you have points. So you have red ones and blue ones. So this is nonlinear. To separate it, it's nonlinear. So what kernel machines would do, what supervector machines would do is they will project that in 3D. In this case, this is a 2D space, obviously, but to project it, it would correspond, it's exactly the same as if I try to bend, I don't know if I will manage, but I'll try to bend this in a way that it's in 3D, and then this will be my hyperplane. You see, it's flat, so it's a 2D plane. I will try to basically come here and cut, which will be the equivalent of finding, taking my planet, separating, and if I did things well, okay, this is a bit messy, but it kind of worked. You go back to the 2D, and then boom! Wow, how impressive! I know. So it's really what it does in real life, and you can do it in any dimension, and it works very well. So many kernels exist. A very famous one is the Gaussian kernel because it uses a Gaussian function, obviously a normal function. And it's very non-linear, so it works very well, but you can use a linear kernel if you want. You can use a polynomial kernel, whatever. There's a lot of people that try to analyze different kernels. It's very good, it's very performant. The problem is it's sensitive to outliers and to the format of the data. If it's categorical, if it's not categorical, you need to put it in a certain, in a certain format. And it's hard to optimize because it has many parameters. It can have 2 to 3 parameters depending on the kernel you're using. So you must be aware of this and use k-fold cross-validation, for example. But otherwise, it's very powerful. Then decision trees. So what is the idea of decision trees? It's very simply to transpose a tree idea to the data. So let's say this is a tree for decision making on detection of a tumor. So it basically allows you to decide what to do depending on cases, on binary cases. So let's say you detected a lump by self-exam. If no, then you do an exam later. If yes, then it's suspicious. The mammogram, you go to the right side. Then if the mammogram is suspicious, if no, then no biopsy. If yes, you go to the right side. Then you see if it's malignant or not. Yes, no. So what this method will do for data is the same as this, but the binary decision you make will be basically the same as splitting the decisions by making a threshold on the data. If the value of a feature is smaller, you go left. Otherwise, you go right. So when you train, you separate the data in linear subspaces by a series of consecutive splits that will make a threshold on the x value. I will show you an example after. You'll understand it better. And then you extract the majority vote in each subspace. Meaning, after you separated your space in rectangles, the most frequent class will be the prediction for points that arrive in these rectangles. So that's what I said, exactly the predict part. So if I show you an example, again, if we go back to our example of people without Parkinson and people with Parkinson's syndrome. So let's say the blue points are with Parkinson's syndrome, no, without Parkinson's syndrome. It doesn't make a big difference. And the red points are with. this is the first node of my tree. It has all the points here. Okay. What I will do is I will try to cut vertically or horizontally, which corresponds to put a threshold on x2 or x1 to separate my space in multiple subspaces. So I do it once. I put a threshold on x2. So let's say x2 is this direction. If it's smaller than 1, I go under. If it's over, it's over there. So this node will include all the points that are under the line. This node, all the points that is over the line. Okay. Then I do the same for this point, but this time I separate it with respect to this line, and then the left one is going to be the points under, and then the other one is going to be the points after. I do the same. I can do it vertically, again, and then basically what happens is my points are separated into rectangles, subspaces, that are as coherent as possible. So you see in this case, S5 is going to be a dominantly red corner. S4 is going to be a blue, blue, red, and red. And then what I'll do is, when I have a new point, I will take my point and go through the tree. If x2 is smaller than 1, I go left, otherwise I go right, etc. And then, depending on where I fall, if my points, when you follow the threshold, ends up in S2, it means that it will be in here, and the average vote in here is blue because you have a majority of blue points. Okay, so that's really how it works. It's very fast, it's easy to optimize, the parameters are not super sensitive, and it handles outliers very well, and mixed outputs, and mixed inputs, sorry. So it's very good. The problem is, it might have a low precision, the regular decision trees. It's quite basic, depending on the format and depending on the data. So you can improve it by doing what's called random forest, which is, instead of training one tree, you train multiple trees, and you add an extra randomness layer. So let's say you have your data, you build, I don't know, let's say 100 trees, which will be trained based on bootstrap samples. So if you don't know what bootstrap samples are, it's basically you sample from the data with repetition. So it might have points, you might have points that are repeated in the data, but the distribution will be the same. So all these trees are based on, are trained on 100 repetitions, let's say, with the same distribution of the data. The problem is they're correlated. When you add this extra randomness, it's the random from the random forest is just in each node, instead of considering all possible variables to cut the node, you just choose randomly m features out of this. And just this randomness factor is going to decorrelate the trees, and it's going to make it better because it's going to reduce variance, so make a better performance. So this is how you train, and then when you predict, you do exactly as you would do in normal trees. You pass your points through the trees, through all of the trees. At the end, you have your prediction for each of the trees, and then you average the prediction, or you take the most frequent vote classification. Okay? It has all the good points of normal trees, so it's very fast. It's easy to optimize. I mean, depending if you take a forest with 1 million trees, of course it's not going to be fast. But depending on how many trees you have, and it handles outliers very well and mixed inputs. It's very performant. And a good feature is you can have some interpretation. So you can extract some uncertainty because this is all probabilities basically. You can really do statistics on each. Instead of taking the average of the prediction of each tree, you can draw the distribution from the trees. And you can also have something that's called variable importance or feature importance. Will tell you what feature was important when you did the prediction. So this is also a useful tool. One problem is that because of this randomness here, and because of the randomness of the bootstrap also, the results are slightly different each time. So you might want to do it multiple times and average the results. And it's still, I mean, I said that just because random forest is one of my favorite methods because it has many good points. It's still maybe not the best, maybe not the best prediction performance. Neural network might be higher. But besides this, it's very useful for a lot of things. So these are just examples to make you, so that you can compare a bit the methods. This is from Scikit. So the bottom one is a very linear case. You can see that you can almost draw a line here. So you have nearest neighbors, linear SVM, which is the first case when it's linear and separable. RBF SVM is the Gaussian SVM, so it's non-linear supervector machines. Decision tree, random forest. So in this case, they all do pretty well because it's linear. So you have the error on the bottom right, so 95% for almost everything. It's okay. In this case, it's non-linear anymore, so it will be harder. Nearest neighbor does a pretty good job, depending on how many neighbors you take. It does a pretty good job. You see, it can do very non-linear things. Linear SVM does very bad because it needs to find a circle and it can only fit a line, so it's not going to be very good. And the other ones are doing quite well. Decision tree, not really, because as I told you, it's not really the best for some cases, and circles are cases where it's just not good, so 80%. And then this is a typical toy example of a moon-shaped data, where depending on the algorithms, it seems that SVM is the best, and random forest is quite good as well. The linear SVM, of course, is not going to be good for that. So you have a more exhaustive table like this in scikit-learn, which is a very famous library that I will talk about at the end, a Python library. So you can see it if you want. Okay, let's go to unsupervised methods. So remember last time we separated in two tasks. You have clustering, where you want to find groups of points, and dimensionality reduction, where you basically have your data in high dimension, let's say 3D, it's not very high, and you want to go back to 2D. And then if you do nonlinear things, it's called manifold learning. This doesn't matter. So a lot of different methods exist. The k-means method basically separates samples in k groups of equal variance, each represented by the mean within the cluster. I will show you an example, you will understand a bit more. Mixture models is basically you model the different clusters as different. Basically you say that the data is following a distribution, and you have different modes of the distribution. So a Gaussian will be a bell like this. You might have two bells, each bell corresponding to a cluster. So it's really what mixture models does. Hierarchical clustering builds nested clusters by merging or splitting them successively. But I won't go into details for this because there's unfortunately no time. Density-based methods looks for dense groups separated by no man's land, so low density areas. It's really like finding an island, separated by the sea. It's really what it does. It's kind of geometrical. And spectral clustering basically tries to project the data in low dimension. It's kind of related to dimensionality reduction, but it gets a bit more technical. It's related to manifold learning, etc. It's very interesting, but it's a bit more advanced, so I won't talk about it either. So what does k-means do? Basically, the idea is to separate in k equal variance clusters, and then minimize for each cluster C the overall distance between all points and the mean in the centroid in the cluster. So with an example, so basically you choose first the centroid. So the centroid will be the mean of, will be the center of the cluster basically. Then the points, the cluster is defined by the points that is cluster that is closest to the centroid. Then you compute the mean and you change the centroid. So you will understand it better when you have an example. So in here you have these two types of points, okay, let's say, that you want to put in different clusters. You initialize your cluster centroid here randomly, and then you say, okay, the points in the cluster for this point are the points that is closest to this red point. So it's going to be this. Then what you do is you compute the mean of these points, and then you define the cluster center as the mean. It's this, and then you redo the same. You take points that are the closest, and at the end you found your clusters. So it's a very basic algorithm, but it works very well if the clusters are quite separated. It's very fast, so that's a good point. The problem is it's a bit basic, and the parameter that you have to, you have to define the number of clusters, so it can get hard, and it's a bit unstable, and it works only for certain clusters. But it's a very good basic algorithm that you need to know. What's the idea of dbScan? dbScan is a density-based method. So in this case, you want to find clusters that are, again, just defined as dense areas separated by low density areas. So you want to find just points that are stuck together with areas without any points in between. And if you have points in between, they're going to be defined as outliers. It automatically detects the outliers. So I won't go into the algorithm in detail, but there are two main parameters that it uses. Epsilon, which is the radius of the neighborhood. So basically, how far you go around the points to say that it's a cluster, and the minimum number of points in the neighborhood. So depending on how many points you want in each cluster and how big you want your cluster, it will find clusters. So this is an example. Let's say you set, this is an example to show you how sensitive it is to the parameter. Let's say you set the radius of the neighborhood quite big, then it's not gonna find small clusters. It's gonna find big ones. It's not gonna find small ones. If you lower it, then suddenly it finds this small one that was included in the other one before. But then if you put it too small, then it's gonna find subclusters within clusters. So it's not good. But it's really working on density, and it's quite powerful. But depending on the data you have, it can find clusters of any shape. There's no need to define before the number of clusters. It detects outliers. So it's quite powerful. The only problem is it's hard to tune the parameters, and it's only with fixed density clusters. If you have clusters with varying density, it gets more complicated. This is just a quick example on data for where you use different algorithms. So this is DBScan, this is a hierarchical method, and this is k-means. Mini-B k-means is just a faster way of doing k-means. You can see different patterns. So depending on the pattern, some algorithms are going to be pretty good or not. This is the typical patterns of nicely defined clusters. They all do well. But for other types like these ones or like these ones, actually DBScan is doing a better job. Again, this is just another thing that I took from Scikit. You can find it in more exhaustive way there. Then we go to dimensionality reduction algorithms. So again, there are many different types. You have the linear methods. These are the two main linear methods that I will show you very quickly. I mentioned them last time during the questions, I think. And you have nonlinear methods. I made a quick list here, but I won't go through them because there's no time. This is just a way of showing you the difference between a linear and a nonlinear methods. If this is your original space, this is the projection by normal PCA, which is principal component analysis, which I will present in detail after. It basically doesn't do anything. But if you use the kernel PCA, which is the super vector machine version of the PCA, then it really separates the two in kind of the same way I showed you. So this is why nonlinear methods can be useful. What is PCA? You probably heard about it, principal component analysis. You basically just project the data in the directions of higher variance. That's really all it does. So let's say you have a cloud of points like this. You first pick the directions where you have the highest range of values. That's where your variance is higher. So the first direction is obviously this one, and then the second one is this one. And then you're going to project basically the data into these two directions. If you're in 2 dimensions, you will just reduce to 1 dimension. So you will project it in the first principal component, so in the first direction of highest variance. So it's like in this case, you just take your points and you project it back to the line. Okay, I did it for real data just to show you that it works the same. This is just 2D points. The main direction is obviously a horizontal one. When I apply PCA, it's exactly what it does. Okay, and you can do it in any dimension, obviously. Another method, it's called multidimensional scaling. So the idea of the algorithm is just to look for a low dimension projection. So it's the same as PCA, but the idea here is to preserve the distances between the points. So you don't want to, you don't really care about the variance. You just want to keep the distances between the points as close as possible. So it's the same as PCA, but it preserves distances instead of correlations. Basically, that's what it does. So I did a quick example where I just wrote DESS, which is the name of our department, with points. Okay, so this is in 2D. For the purpose of the toy example, I just projected in 3D, okay, in a random direction, and then I projected back in 2D with MDS, and you can see that basically the distances between the points are preserved, and you can read the word. That's really what MDS does, and you can do it in any kind of dimension. Okay, quick examples. I don't need to go in detail with it, just to show you the difference between different algorithms. This is just a sphere in 3D. You can see that you have a majority of red points on the right and blue points in the left, in the left and in the right. You can see that with MDS, it really captures back where the points are and keeps the group together. But in PCA, it doesn't, because actually the biggest dimension, the biggest variance is in this direction. So it basically projects everything this way, and the blue and the red points are getting kind of stuck together. But otherwise, you know, it works. It's just, it doesn't do the same thing. And this is for the S example. You can see it later if you want. It's not very important. Okay. The important thing is deep learning, aka neural networks. So deep learning is just basically an assemble of neural network. What is a neural network? It's a highly nonlinear predictive function that is trying to mimic the neurons of the brain. So it's just trying to copy the architecture of the brain, but only the structure, the architecture. So what is the idea of a neural network? You start with a linear function. So you just have this function, a times x. It's stable, easy, and it's fast to compute. Okay, so you have your input here. You just have linear function, so ax plus b output. What you do then is you add a nonlinearity after. So it might be an S-shaped function or a function like this, which is called a ReLU, but it's just a nonlinearity that you add after it. And you repeat. So you have linear function, nonlinearity, linear function, nonlinearity, and when you put that together, it makes a nonlinear function. And it's quite powerful, and it's a very easy idea. And you can have multiple neurons on top of each other. This is the typical structure of a neural network. So you have your inputs here, you have your neurons here, and you have your output here. Okay, so each value at the beginning is fed to neurons in the middle and then fed back to the output. And for each arrow, you have a linear function and a nonlinearity added after. So this is supposed to, again, mimic the structure of a neuron. So, you know, you have your cell body here, you have the information that comes to the cell body with dendrites, the same way the arrows goes here, and then the axon propagates the information to the output after. It's really trying to copy the structure, but only the architecture. But it's basically a way to do a very big, very nonlinear function. You can have multiple hidden layers. You can add as many as you want, and that's the depth of your neural network. So each arrow has a weight, of course, because it's a linear function for each arrow, and the idea is just to find the weights. You just want to optimize the weights, and at the end, you have something that is very, very nonlinear. So what is deep learning? Why do we call it deep learning now? Because the neural networks got larger, deeper, and we have the power to use them. For example, for image processing. So if you want to have, you want to recognize whatever kittens from dogs, you just put that as an input, and it will try to find basically features that will say, okay, at the end, it's a kitten. It's a very efficient representation because it's basically a nonlinear function made out of very, very simple functions, linear ones, and we know how they behave basically. If you make the models deeper, so if you have a bigger number of hidden layers, you don't have to use as many parameters, which are the weights of the linear function, but it's also powerful, and it can theoretically learn anything. It's like, it's just a combination of very simple functions, but if you add enough nonlinearity, it can model any kind of function. There's actually a mathematical theorem that says this, so it's quite powerful. The problem is you need to find the right architecture to model it. And basically, okay, it got crazy. In 2015, this is numbers of 2015, people were doing neural networks with like 15 to 25 layers and 100 million parameters, just to tell you that, okay, now it probably doubled, and you need GPUs and powerful computers, but otherwise, it works very well. So why is it so powerful? Why is it so famous nowadays? Because again, it's powerful and versatile, it can do anything. from clustering to supervised learning. You can model anything, and it's very good for famous applications like text, or audio, image, etc. Let me remind you that neural networks are a very old idea. So the thing is, it works now because we have more data and more power, like I said last time. But this is important. So it's extremely performant, probably state of the art. It's very versatile. The problem is it requires a lot of data and a lot of work, because you need to decide the architecture, you need to tune a lot of different parameters, and it can take a week to train. It can take a very long time, even if you have a huge computer, because if you have 100 million parameters, it's just going to take a long time. So it takes a lot of work, but at the end, it can be worth it. The different types of deep learning algorithms, well, there's so many. The multi-layer perceptron is the one that I showed you, kind of. Convolutional neural networks are used for image processing. So, for example, to detect letters. This is just an image from a very famous paper by Yann Lequin, who works at Facebook now, who worked on this. But it's very powerful if you want to know about image processing. Convolutional neural networks are really the thing to do. And then for time series, for example, you have things called recurrent neural networks and LSTMs, long short-term memory networks. You can look into them if you want. It's very useful. It's very powerful for time series prediction. You have thousands of them. I found this randomly. It's just, there are so many different types. And it's state of the art now, so everybody wants to work on it. But yes, even from the simpler one, it can be very powerful. A quick section on how to choose the method. So obviously, it depends on the goal of what you want to do, on the amount of data. Some models need more data than others. The types of format you have. Some models can handle any kind of format. Some models cannot. So then you have to work a lot on it. Do you have features that you want to interpret the importance of the features? Do you want to have a small number of features? Again, depending on the model. And how much do you want to interpret? Some models, like deep learning, are hard to interpret. Some other models, you can have some importance, like for random forest. Ultimately, you want to try different ones and see, which one works the best. But you still have a guide from the beginning to see where to go. So this is a guide taken from scikit-learn that you can see after if you want. It basically, follows a little path, and then says, okay, depending on the amount of data, the type of data, etc., it will bring you to these different, we all saw classification, regression, dimensionality reduction, clustering, different kinds of method. This is quite useful. It's not universal, but it's quite useful. So yes, finally, a very quick bonus on imbalanced data. So in public health, you have a lot of cases where you have data that is imbalanced. Let's say, for example, you have 5 patients with cancer and 95 healthy patients without cancer. Well, there are some methods to solve this issue, which is that if you have so many zeros in your data, the model will try to say, okay, they're all zeros. It will make it life easier, and it will just make it better. So the solutions for that are many. You can undersample, meaning take out some majority samples. You can oversample by creating new minority samples. You can add weights, or you can just play with the probability threshold, like I talked about last time with the ROC curve. This is an example of a technique that is quite useful. It's called SMOTE, which just artificially creates, so let's say in this case you have more rectangles than circles. Well, it creates, fake data, but that is in between the existing points, so that it has kind of the same distribution. And then you work on top of this. It works quite well, not for everything, but it works quite well. Okay, very last thing, code. So what should you do for code? Am I short on time? Still have 1 minute. So you have many libraries, but I will be very fast on this. For general machine learning, I know Python, so that's what I know. Scikit-learn is very useful, so if you use Python, I recommend it. In R, you have a library called Caret. For deep learning, these guys are not very good at deep learning. So you have TensorFlow and Keras, which are other libraries. And if you just don't want to know which one to take, yes, you can just download this it's like a meta library. It's a library of libraries called Anaconda, and there's everything in it. So if you want to start, just download it on there. So scikit-learn is very useful because it covers almost everything but deep learning. It has a very good documentation with examples, and it even has a theoretical portion. So if you want to know more about things, this is just an example where I show how to train a random forest, but just to show you that it's very fast, basically. This imports the libraries. This creates synthetic data, and actually it's just this who trains and measures the discrepancy, the accuracy. So it's very fast. You may want to optimize it better, but in this case, it still works because it's 96% accuracy. Okay, so this is the end. What have we done? What have we seen? So a lot of different models. So it may be a lot of information, but I just tried to show you the main ideas of, kind of basic and important models. So we saw concepts for classical predictive models, and we saw deep learning. There's a lot of things that I didn't cover, about a lot of different applications, natural language processing, etc., etc. A lot of different machine learning methods. But you can look for them if you're interested. And I hope, yes, it motivated you to know more. The next presentation will be in September 23rd, and it's in 2 weeks, something about visualization. So yes, I'm out. This is the end. Some references if you want. Thank you, everyone. I am on time, almost.
Thank you very much, Dan. So a lot of information.
Yes, yeah. It's a bit more dense than the first one. I apologize for that.
But we'll have the slides afterwards. So
yes.
Thank you very much for all these details. So just one question on the chat. Are there any packages for Stata?
Oh, no, not Stata. There should be. I'm really not a Stata expert. There should be, probably. But to be honest, I don't really use Stata. Maybe I don't really use Stata, so I don't really know. You obviously have a lot of, traditional statistical functions. I'm pretty sure you should have some machine learning things, but I'm not sure.
Okay. So, also regarding R and Python.
Yeah.
What do you recommend depending on the application?
R was really designed for statistical analysis, so it has all the statistical functions you can imagine, but it has also some machine learning libraries. I think Python is a bit more volatile because it can really do everything, and that's the one I know. So and it's very. I mean, if you don't know neither R or Python, I would say it's my personal opinion. It's better to learn Python because you can do everything in it, not just statistics and not just machine learning or prediction. You can do everything in it, and it's really documented. Like you have many libraries about anything. So if you're going to learn a language, you might as well learn Python. And I know that scikit-learn is really documented and updated daily, and it's really the #1 machine learning application I think across everything. So yes, I recommend Python. The language, the syntax also is very intuitive. R is fine also, but maybe you have some small differences, but they're quite close to each other. So if you learn one, you should be able to learn the other in any case. So, yeah.
Thank you. Just also one question. You talk about neural network for text.
Do
you have some more examples, or which kind of neural network is used for text?
I mean, it's not okay. It's not the let's say most neural network. I mean, the most famous ones are maybe more for speech and image. But I'm pretty sure you can do things with text. Like for example, I mean, when I say text, it might be an image of it might consider the text as an image and use CNNs like convolutional neural networks to try to detect shape of the letters, etc., etc. But then of course there might be some applications, but I don't really for example the traduction like Google traduction, this kind of things. I'm pretty sure there's still deep learning behind. It's just, there's also DeepL, you know DeepL, which is like a famous prediction thing. It basically gathers so many information about so many languages, etc., and try to learn from it. And it's basically like supervised learning, but if you have like a huge deep learning net, it's just very powerful. So yes, but I don't have, you know, clear examples to give you more about text. It's really not my specialty. So.
Thank you, Dan. Another question in the audience?
I would maybe general question about clustering. It's an interesting method, and I have sometimes tested it for some data. But is it anyway that it doesn't guarantee that you get kind of answer what you want? Those clusters maybe don't always match your problem. So it's really anything to do in that case.
Well, I mean, you know, the first thing you need to do after you found clusters is to go within the clusters and see if they make sense. You see if they match your expectations. But you mean if you just apply a clustering algorithm and you just find random clusters that you don't want? That's what you said?
Yeah, I guess that if you are like predicting some disease or something, those clusters maybe are something else, but nothing to do with the disease.
Yeah. Well, you make bad clusters. I mean, you know, the data tells you something, but then you might have a certain arrangement of the data so that, you know, you find something that is a bit strange, or maybe just your parameters were wrong. You should. I mean, when I do clustering, I like to visualize things. So even if I have a huge dimension, I like to use some kind of PCA or whatever to see, because otherwise you don't, you know, you don't know if you had good clusters just from the data if you don't see the data. So if it doesn't make sense, it means that something was wrong, probably, or the data is very weird. Yeah, that's all I can say, kind of.
Okay, thank you. So there is no other question. There is just one answer from Leonard about the text that can be considered as a time series. So
right, yes. Yeah, so I guess LSTMs and this kind of things are very useful. Yeah, sure.
Okay, so if there is no other question, so we close the session for today. Thank you again.
Thank you. I hope you managed to follow kind of, I know it was a bit of a lot of information, but thank you very much.
Goodbye, everyone.